Okay, thank you. Thank you.
You would win by yourself. It happened. It happened. He got on my turn. Where is
We're gonna review. We're not really gonna write. We're just gonna review a couple things. Okay. All right. Here we go. Here's the plan. Let me explain. Kind of. I got the lab as much as I could. I got the lab. I believe I got the lab 3 days next week for you guys, which is a lot. Given the fact that we're Oaks testing and it's. I mean, I had to took practically an act of Congress to get the lab for even 1 day, but I got it for 3 days for you. That's for next period, isn't it? I think so.
No, that's right.
If you need to. I think it said, didn't it say 6 on it? Oh. Okay. Go. I mean, yeah, if you need to go see what it does. Okay, so anyway, so you're going to have, here's kind of your time frame. You might be a little bit behind, you know, that's okay. I mean, you're gonna have some time, or a lot behind. But in that case, good thing spring break is coming up. I'm not going to close the tests until after the Wednesday after spring break. So that's like April 3rd or something like that. So that's when they close, or April 5th or whatever. I don't know what day it is, but it's the Wednesday after spring break. They close. You have to be done by then, or you're going to be in bad shape anyway. I mean, it's not going to work for you. You'll have to find something else to do. You just got to get that thing done. You can. Most people are in reasonably good shape on that. The reviews, you got to get those reviews done. You're going to have this weekend to work on them. I've got all the resources up there. I will rename all of this was a good suggestion. I can't remember who made this, but it was a great suggestion. On all the PowerPoints, I will change the names so they say like 5.2, and then it gives you the title. So you know which sections in the book they go with, right? Okay? If anybody doesn't have a book, I think everybody does, but if you don't have one?
I don't have one.
Okay, so I want to get you one today. Okay, so at the end, let me sign one out to you. I want you to have them this weekend to look at. The YouTubes are all up to date. The PowerPoints are all up to date. We got 3 days next week to test. I'm getting period 5 for, actually I think I tried to get them for today, but it wasn't available, of course, because of the assembly. So I'll get you guys for Wednesday next week, the whole group for TA. Okay, that'll be your day to be in TA and have questions ready to go. We'll be in the lab Tuesday, Wednesday, and Friday, I believe. Those are the days I can get it. Sweet. So what I want to do now, though, we have a responsibility to ourselves not to get, I mean, we got to be on track to get through the material we need to get through. So this is really not a bad thing to start with. This is the new unit, no harder than chapter 5, maybe easier. But it's stuff it's real algebra. I mean, this is not stuff that we were doing earlier in the year. This is real algebra like chapter 5 is. I mean, it's, you know, higher order polynomials. But the first section is just all review. All it is just a review of properties of exponents. Stuff you already know, but I want to just remind you about it. Let's put all the phones away. Jacob, put that away, please. Phones and any distractions need to be completely away. Thank you. This is just it's a real simple review of stuff you already know. I want to help you review it, and I want to maybe improve your understanding of it. Give you some hints that might improve on what you've learned in the past a little bit. So let's go with this. All right. Properties of exponents. Okay, so first of all, the properties of exponents, we're going to go through a whole list of these things, but in this list you need to understand what the stuff means in the list. What are the A's and the B's, and what are the M's and the N's? So A and B are just any real numbers. So what does that mean? What's an example of what A and B? Give me an example of what A could be. Could be 1. What else could it be? 2. Okay, good. So it could be whole numbers. What else could it be? Give me another example. Say it again. I don't want other whole numbers. Give me something different.
3/4.
1/2 it could be, or 3/4. They could be rational numbers. They could be integers. They could be negative, like -4, -5, right?
Yeah.
What else could they be? We got fractions. We got rational numbers.
0.25.
Say it again.
0.25.
Could be 0.25. That's just a decimal equivalent of 1/4. What else could they be though? Even things like, what's a weird one that we haven't gotten yet?
5/8.
5/8. Okay. Another fraction. What's another kind of an example of a problem? I mean, you've done some of these already in chapter 5.
Square root.
Square roots. Sure, we could have something like the square root of 2. or the square root of 3. Answers that you can't write as a fraction. If you wrote them as a decimal, they would go forever, right? They never repeat, never terminate. We could even have like pi or something like that. So anything that doesn't have an I in it is fair game, right? Now, m and n, these have to be integers. What are integers? Negative and positive whole numbers, right? So it's going to be on a number line, they would just be the dash marks on a number line. Okay, so if those are what the numbers mean, now let's look at the properties that they represent. So the first one, this is one you're real familiar with, the product property for exponents. I don't care if you know what it's called, it makes no difference to me at all. I just want you to know what these are. Fill in the blanks. I'll start the statement, you fill in the blank. When you multiply like bases, you what the exponents? Add the exponents. You've heard that a million times, right? When you multiply like bases, you add the exponents. So the way we write that, algebraically would just be a to the m times a to the n equals a to the m plus n, where a is the base. Could be any number, any real number. M and n are just integer exponents, right? And so that's always the case, right? Make sense?
Yep.
Okay, it turns out, by the way, that, I don't really like this. We don't need to even restrict these things to integers. They don't even have to be integers. They could be fractions, for example. And then we'll deal with that later on in the year. So what's an example of this? So if we wanted to do something like, let's say we wanted to do something like 3 squared times 3 cubed. What do we get back? 9 to the 5th. Good. No, but not 9 to the 5th. Sorry. It's not 9 to the 5th. No, it's not. I was listening to what you're saying, but that's not right. What is it? It's not 9. It's 3.
Oh. So 3 to the 5th.
It's 3 to the 5th. The base stays the same. When you multiply like bases, all you do is add the exponents. The base stays the same. Okay? Now go ahead.
What if a is 2 different numbers?
That's what I'm going to do next. Good. Okay, so look at this. Now, how can you sort of conceptualize that? What does a squared really mean? Well, 3 squared. 3 squared really just means 3 times 3, doesn't it? Right? What does 3 cubed really mean? That really just means 3 times 3 times 3. So if I multiply all those out, don't I just get 3 times 3 times 3 times 3 times 3? Right? Well, 3 to the what? 5th. Right? Does that make sense now why it is the way it is? Okay. So what about then, Kyler had a good question here. What if we did something like this? What if we did instead 2 squared times 3, 3 cubed, let's say. What's that simplify to? You can't do it. I mean, we could turn those into numbers and multiply them, but there is no property of exponents that work there because those are not like bases. So you can't combine them that way. It only works if you have like bases, right? That make sense? Okay. All right, so moving on. So that's the first one. You already knew. Here's the next one that you also already know. I don't care that you know the title of this. Once again, it doesn't matter to me. This is power of a power property. I don't care. All it is this. You fill in the blanks. If I take a power to a power, what the exponents? Multiply the exponents, right? So look at the difference now. Compare what we just did. If I have something like, we won't even use 2's. Let's just use like x's. How about? By the way, sometimes you think, oh, darn it, we got more variables. Let's just stay with the numbers. Wrong. For this stuff, exponents are so much easier than numbers. You'll agree. I promise you'll agree. X squared times x cubed equals x to the 5th, like we just said. X squared cubed equals x to the 6th. Yep. Okay. Make sense? Yep. Okay. And really, there's a way we could represent that also. See if this makes sense. What does x squared cubed really mean? Doesn't that just mean x times x times x times x times x times x, right? Something cubed just means that something times itself 3 times, right? If the something is an x squared, well, that's what we get. How many x's are there? 6. So it's x to the 6th. Okay. Okay, what about this one? Power of a product property. Let me go back a little bit. I don't want to get too much up there at once. Power of a product property. Okay, this one. Now, I want to say something really important about this one. Okay, this is a pretty easy one. You know this one too, and you've used it. So if we have something like, for example, if I have something like the quantity 2x squared, what this tells me is when I have a product to a power, I can break that into the product of the separate power. In other words, I can distribute the power to both of the factors that are being multiplied. So that just equals 2 squared times x squared equals 4x squared. Okay? Okay, here is what you cannot do. You can't overgeneralize with this. This is a really common mistake that people make in algebra is then they want to say, okay, well what about something like x plus 2 squared? Is that equal to x squared plus 2 squared? No, it is not. You can't do that. It only works for products, not for sums. What is x plus 2 squared? Think about what that means. X plus 2 squared equals x plus 2 times x plus 2. And if I FOIL that out, I'm going to get a lot more than just x squared plus 2 squared, aren't I? Right? So it doesn't work for sums. It does work for products. Okay? Questions? All right. Okay, the negative exponent property. Okay, this is another one that you probably haven't used a ton, but I know you've seen. This is the one that says a negative exponent is equivalent to a positive exponent in the denominator. Okay, but I'm going to make this, we can expand this so it's much more useful to us. Instead of just limiting ourselves to that, we could say something a little broader. It's more helpful. We could say this. Okay, sure, a to the m equal, or a to the negative m equals 1 over a to the m, but also 1 over a to the negative m, what do you suppose that equals? A to the positive m. So we can say something much better about this. Here's a better way to remember this one. A negative exponent in one part of a fraction. And by part of a fraction, there's only two parts, aren't there? The numerator and the denominator. So a negative number or negative exponent in one part of a fraction always means a positive exponent in the other part of the fraction. Okay? So for example, and there's really just a 1 on the bottom there, isn't there? Right? So a negative exponent in the numerator is equivalent to positive exponent in the denominator. Negative exponent in denominator is equivalent to positive exponent in numerator. Okay? So then, so what's this then? What is okay, that's going to be equivalent to 2 to the positive 2 on the top, right? Which is what? 4. Good. Okay, there's another little trick that goes with that. If I have a fraction, and this isn't in the book, but this is a really helpful one. This will help a lot on the assignments. If I have a fraction like a over b to the negative m, okay, what does that negative sign do to that fraction, do you suppose? What's it do? Think what it did up here, and we'll come back and look at this from a different perspective in just like a minute. But what did this really do up here? A to the negative m on the top just gave us 1 over a to the m. So it really just gave us the reciprocal of a to the negative m, didn't it? See, or the reciprocal of a to the m. See what I'm saying? Same thing here. 1 over a to the negative m gave us a to the positive m on the top, which is just a reciprocal, right? Suppose that works for fractions with numbers other than 1 on the top and bottom? Yeah, it does. So this is just equal to, if I have a fraction to a negative power, it just equals the reciprocal of that fraction to the positive power. Knowing that makes these problems a lot easier, really. That's very helpful. Okay? All right. So Okay, this is a real simple one. It never changes. There's not much you have to ever do. The zero exponent property just tells us that anything other than zero itself to the zero power is always equal to what?
Zero.
Nope.
One.
1. Always. Doesn't matter what it is. I could give you the most complicated thing. I mean, we could do something like if I told you 2x squared plus 3x to the pi minus the square root of 9 plus x, whatever, to the zero power, doesn't matter. What's it equal? 1. Guaranteed. Okay. Always. Anything to the zero always equals 1. Okay. And then the last couple things are freebies. They're just the equivalents of stuff we already did, but instead of for products, just for quotients. So instead of multiplying, we're dividing. So for example, the quotient of powers. Well, we said that when we multiplied like bases, we added exponents. When we divide like bases, we subtract exponents. And I'll show you why. You can always remember that. There's a really easy way to see this relationship. If we combine two of the properties we just talked about, remember we said two things. We said a to the m times a to the n equals a to the m plus n. Look, that's supposed to be an n. If we add that concept to concept number 2, a to the negative n equals 1 over a to the n, right? Then you tell me, how could we combine those two concepts and come up with a formula for a to the m divided by a to the n?
The bottom would be negative.
Okay, so I could write a to the n on the bottom as a to the negative n on the top, right? That make sense? So we could write that as the product of a to the m times a to the minus n. And what does our product rule say? If we multiply like bases, we what? Add the exponents, right? So then this should just equal a to the m plus negative n. But what is m plus negative n? Just m minus n, right? So that's just equal to a to the m minus n. And so there is the quotient of, I don't know what they call it, quotient of bases rule or some quotient of powers rule. I don't care what it's called, doesn't matter. Here's what you gotta remember. If we divide like bases, we subtract the exponents. But here's an extension that really helps. It's not in the books, but this really, really helps. This is also true. It's also equal to 1 over a to the n minus m. Now, why would you do that, you might ask? Okay, here's an example that illustrates why you would do that, why that's so helpful. This one's pretty obvious. If I had something like x to the 7th over x cubed, what are we going to get back?
7 minus
X to the 7 minus 3 equals x to the 4th, right? No big deal, okay? What about this one, though? What if we have, instead, what if we have x cubed over x to the 7th? What's that equal to? X to the 3 minus 7, which is x to the negative 4. But the assignment is specifically going to ask you to always write your answers in terms of positive exponents. So what else would we have to do to that?
We'd have to do the next step.
Got to put it on the bottom. Good. So we'd have to write that as 1 over x to the 4th, right? Okay. Now look at this little trick I showed you, how helpful this is. Instead of doing that, you could just say, okay, 7 is bigger than 3, so here's the rule you use. When you're dividing like bases, you always keep the base where it has the most power and subtract the other exponent, right? So we could just directly say, okay, that's equal to, the x stays on the bottom because 7's bigger than 3. And on the bottom, we get x to the 7 minus 3, and so we just get 1 over x to the 4th in one step instead of 2. Okay? Make sense? Okay? And then the last one is another sort of a freebie. This is no big deal. It's exactly what you would expect. It just says that if I have a quotient to a power, I can distribute to both parts, right? That works just like it did for a product. You just can't do it when you're adding or subtracting, but you can do it when you multiply or divide. I can distribute the exponent, okay? So that's all there is to it. Now, let's just maybe look at a couple quick examples. Okay, so just get your bearings on that now.
Can you go back like 5 seconds?
Sure. And if I don't, I can't remember if I already have this one up online, but I will put this up for the weekend too. Okay, just in case you want to, start looking at this stuff. Okay, is everybody good? Okay. Okay, so what about this one? Now, what's the property that's going to apply here?
I don't know. It's multiplication, so you add the.
Okay, look, yeah, notice that we have like bases here, right? If we multiply like bases, we just add the exponents. That's all we're doing, right? So, we get -5 to the 4 plus 5, -5 to the 9th. That's a big number. Okay, that's what it is. Now, you might ask, okay, could you do this without properties of exponents? Yeah, you could. We could just take -5 to the 4th, get a number, multiply by -5 to the 5th. We could do that, that's true. But you can't do that with things like exponents, for example. Okay, then you have to use these properties, okay? Another example. What is that doing? That's kind of a strange one. I don't know what that was supposed to be. Okay, what about this one?
2 to the 3rd plus 4.
We take a power to a power, what do we do?
We
So
can
do the
get into
job.
both of them.
Say it again?
Distribute.
So well, you could say 8 to the 4th. You could. For numbers, you could. You're right. We could also, if we want to write this as a power of 2, what would we do? Right? It'd be 2 to the what? Is it 2 to the 7th or 2 to the 12th? 2 to the 12th. Because when you take a power to a power, you multiply the exponents. Okay? And that's going to be a big number. That's 64 squared. So man, that's a big number. 3,600, like 3,700 and something. 4,090, big number. Okay. Yep.
The Google and that number.
Google.
Yeah.
Google. Google's 10 to the 100. Big number. And a Googleplex is 10 to the Google.
Those are numbers?
It's a 10 followed by, be a 1 followed by a Google 0.
Those a number?
What?
And a Googleplex is 1 to the Googleplex 0.
Is
So,
there anything apart to that?
well, there's no limit to how big numbers can be. Infinite.
Numbers aren't real.
There you go. Okay, so what's that going to be?
Same thing we did last time.
Yep, 3 to the
8th.
8th. Good. Okay.
And you did your ring.
Okay, we did. Didn't we do? Oh, wait. Okay, yeah. What's that one going to be?
-5.
-5 to the what? To the -2, right? -6 plus 4, right? Now, what's -5 to the -2?
1 over negative
5 to the
2.
2. Good. And what is -5 to the 2?
25.
25. So it's 1/25. Okay. All right. You're getting it. Okay. This makes it easier. Exponents make it way easier. You don't ever have to get your answer is just property of exponents, and that's it. Yeah, so that's going to be x to the 5 minus 3, right?
Yeah.
So x squared, good. Okay, now what about this one? Now we're combining, well, actually we're not actually. What's that one going to be? A couple of them get combined.
R is like it.
Okay, so we have a quotient to a power, so I can distribute the r to both parts, right? Okay, but something's still funny about that. We want to write it in terms of positive exponents. So it goes on top.
Yeah.
So we have r squared s to the 10th. Okay?
What? Wait.
Okay? That's how you write it. Yep.
And same thing if we got two different numbers, right?
You just do it because,
What's that?
you just do it because you need to.
Well, no, you'll see there'll be, I mean, what's the context of doing this, you mean?
Yeah, like,
Well, okay, so for example, when we multiply polynomials, let's say we're multiplying an x cubed term times an x cubed term. Well, we gotta know what's that mean. What do you get for a power, for example? Okay. Okay. Try to think about that one for a second. And you gotta just kind of organize your thinking on this. And you're following just order of operations, right? There's nothing you can do inside the parentheses. What about that?
7b to the 6.
So what's it gonna be?
7b.
7b to the what? Oh, you did the whole thing. You did the whole thing. Yeah, that's, okay, so you got 7b to the what? Not 4. But you forgot something anyway. You're on the right track. But instead of trying to jump clear to the answer on this thing, forget this part, right? What is just that, what's that first part giving us right there? To the -6, but it's not 7. It's not 7 because I've got two parts here. I've got 7 times b to the -3 to the +2. I have to distribute the squared to both parts of that are being multiplied, both factors. So I'm going to get 7 squared times b to the -3 times 2, right? Make sense? Okay, so what's that going to look like then? That's going to look like 49, right? 7 squared. B to the what? -6 times b to the 5th times b really to the what? First. Good. And so can I add up all three at once? Yeah, I can. That rule of multiplying like bases and adding the exponents applies to a string of more than a product of two factors also. So I'm just going to get 49 times b to the sum of all those exponents. -6 plus 5 plus 1, which is what? 0. 49 b to the 0. What's b to the 0? So it's 49. That's it. Okay? How about that? Make sense? Okay? Okay, now let's do this one not the way the I'm going to skip the PowerPoint on this one. They don't do that. They don't use our trick, our new better trick. What do we do with one like that to get the answer directly? Keep the x on the bottom, right? Because 10 is a bigger power than 5. So you keep the base where it has the most power. So what goes on top then?
1.
Got to put a 1 on top, don't we? And then I'm left on the bottom with x to the -5. Good. So we just end up with 1 over x to the 5th in one step, right? That's good. Now these guys, they don't know what they're doing. Look what they did. Oh, I think I skipped that one. I wrote over the top of that one because they went through a different process. Okay, quick review of scientific notation. Just because of the exponents, that's why this comes up in here. Really simple though. Remember what scientific notation means and why we use it. Scientific notation is a convenient way to deal with really big numbers. And in physics, for example, you deal with really big and really small numbers. There's just all, I mean, like just as an example, the mass of the Earth is about, I think it's 5.98 times 10 to the 24 kilograms. So it's a big, big number. There's lots of those big numbers that pop up in physics all the time. The mean radius of the Earth, I think, is 6.2 times 10 to the 6 meters. And so there's lots of these big numbers that just come up again and again. But it'd be really inconvenient. Think about if you had to write out the mass of the Earth. If you had to write that out without using scientific notation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a big number, right? We don't want to write that thing out like that every time. That's a real pain. So instead we just write 5.98 times 10 to the 24.
What does that even publish?
I don't know what that would even be called. It's darn big is what I would call it. I mean, the way you'd have to describe that, I guess for what it's worth here, that would be, if we break this into pieces, let's see, there's, would So it'd be about 5,980,000,000 quadrillion kilograms.
Ah,
So the Earth is big, right? That's, but the Earth is small compared to lots of
I've
things.
seen bigger.
Yeah, you see that? Okay. So how do we do this trick with scientific notation? How do we take a big number like this and turn it into scientific notation? Right? So it's just a trick with the decimal point is all it is, right? The decimal point starts right there. What are we gonna do? Do you remember?
Go to the first significant digit.
Okay, good. Exactly. So we're just gonna move the decimal over until we're left with a result.
Of just numbers and years.
So we're left with a result that is greater than or equal to 1 and less than 10, right? So does that make sense?
1.31.
So we're obviously going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but that's not far enough because 13 is still not less than 10. So I got to go one more, right? If I go one more than that, I've gone too far because the answer has to be greater than or equal to 1. If I went one more, I'd have 0.1, which is less than 1, right? So we stop right there after going 3, 6, 9,
11.
11 it was, wasn't it?
Yeah. To be 1.
So then we'd say that's equal to 1.314
312.
times 10 to the positive 11. If I counted it right, yeah. Yeah, go ahead, right? So when you see scientific notation, numbers like this, okay, that have a large exponent, those represent big numbers. Also in physics, though, we look at things like, let's say we want to look at what are we looking at? Say we're looking at the average diameter of, let's say we're looking at the diameter of the nucleus of an atom or something. Then you're looking at something on the order of,
Something really small.
on the order of like 1 to the negative 10 meters, an angstrom. Okay, and so that's negative 10 meters. Think what that means. That's a really, really small distance, isn't it? Right? If we write that out, what's that? Well, that is that's a trillionth of a meter. Okay? So you're talking about a really, really small distance. You want to talk about an electron mass, 1.61 times 10 to the negative 32 kilograms. Really, really small. So these are really tiny numbers, and once again, you need scientific notation just as badly for a number like that. So say we want to take something like that.
The prefix.
Say we take a number like, how can I write that in scientific notation? What do I do this time?
Same thing, but backwards.
Okay, I got to move the decimal to the right this time, starting there, until I get a result that's greater than or equal to 1 and less than 10. So 1, 2, 3, 4, 5. You tell me when to stop. 6, 7, 8, stop. So that would just equal 1.35 times 10 to the negative 8, because we moved right instead of left. Okay? Make sense?
Yeah.
Okay? So why do we do this stuff? Well, mainly because it's a convenient way to write the numbers, but also because if you wanted to do what's called, scientists call a shirt sleeve calculation, where you don't have a calculator, you're trying to just think of some rough estimate of an answer, look what you can do. You can take numbers, and you do this all the time in science. You're just trying to trying to ballpark something and figure out what order of magnitude, like roughly how big is this going to be. You don't need to have an exact answer. So say we take something like that. How are you going to divide that out in your head? You're just not going to do it. I mean, it's not, that's too hard to think about. But if you write these two numbers in scientific notation, look what you get. Okay, you get, a quotient of small numbers and a quotient of powers of 10, like bases, right? What's 10 to the 11th divided by 10 to the 6th? 10 to the what? 5th, right? I just subtract exponents. And then 1.314 divided by 1.5, well, that's about 1/4. 4 times 1.3 would be 5.2. Now, it's not exact because we have other decimals there, but if we just want to get an estimate, that's about a 1-to-4 ratio, roughly, right? And so we could write that as something like, I wouldn't even make it that accurate. I would just say it's about something that's roughly equal to 0.25, 1/4, times 10 to the positive 5th. Is that a good way to write that in scientific notation, though? What's the one thing we probably have to do there? Where does the decimal point need to move?
Yeah.
It's got to move 1 to the right, doesn't it? It's got to move 1 to the right. So if we're making the number out in front bigger, we got to make this number smaller by 1, right? And so we just end up with 2.5 times 10 to the 4th. And when you work with numbers at all, often, frequently, 10 to the 4th, that just means 10,000. 10 cubed means 1,000. 10 to the 6th just means 1,000,000. You just get used to those numbers real easily. And so that's just 2.5 times 10,000 is 25,000, right?
Yeah.
Okay, so you can do that really quickly. Just scratch out an answer without having to ponder how to do long division on those huge numbers, right? Okay, that's good for today. So we got, how much time have we got here?
2 minutes.
Okay. So what